So thanks to the organizers for giving me the opportunity to be here. And thanks, Jerome, for that great introduction. So I get to skip some of my introductory stuff, or maybe reemphasize it. So if you look at the title of my talk, I'm trying to talk about what's happening in cardiac energetics during heart failure. But I want to talk a little bit about physiological cardiac energetics, because I'm going to claim that we can't understand the pathophysiological state until we understand the physiological state. So essentially what we're trying to understand is how this system is controlled and regulated in vivo. This is synthesis of ATP from the substrates inorganic phosphate and ADP. There's this exchanger, ANT, which Jerome was telling you about. And then in the cytoplasm, this ATP is hydrolyzed into phosphate. Now the big idea, and this is where probably almost 30 years ago there was a split between the cardiac and the skeletal muscle community on this. The big idea in the heart is that this system is somehow or another controlled without feedback. Okay, so just to read this, a little bit of this quotation: the data that exist in vivo imply that a simple feedback model is not adequate to explain the regulation of energy metabolism in the tissue. So we started off in trying to build these models with one of the goals of trying to understand how can this system be controlled without feedback. That is, feedback signal, you would think of the feedback control that's apparent in vitro is that as you add more of these substrates, this mitochondria and oxidative phosphorylation system is upregulated, and of course as you synthesize more ATP, well, then you eat up that signal. Okay, so people that are in this room that are probably smarter than me would know from reading this quote that how can this possibly be? And the answer is it can't possibly be. And that's what we're going to discover, or we did discover. So looking at the data a little bit, and these are some of the same kind of data that Jerome showed, but these are from heart, steady state data, creatine phosphate as a function of rate of oxygen extraction from the heart. And all of these data come from our collaborators, Jay Zhang's group in the University of Minnesota. These are all anesthetized dogs. So here's the creatine phosphate signal. Here's the inorganic phosphate signal as a function of steady state MVO2. So inorganic phosphate goes up. Here's that transient experiment, similar to the skeletal muscle experiment where the LAD is occluded transiently, and then you get this hyperemic flow recovery here. And here are the measured data. The creatine phosphate goes down, the phosphate signal goes up. And so this is the same experiment that Jerome showed. But I will say, and by the way, our solid lines are model predictions. These are not model fits, they're model predictions. We did have to replace that phenomenological Klingenberg model of ANT with an updated, more detailed mechanistic model in order to get these model predictions. But the models are all parameterized based on in vitro data, all coming from kinetic experiments on purified mitochondria. So these and the other data are consistent with our hypothesis, which replaces the metabolic stability hypothesis of Balaban. Balaban's idea is that this system is controlled without feedback. Well, we can explain all of these data with a model where the phosphorylation is controlled primarily by feedback through inorganic phosphate levels. Okay, so, and you can read about the details in these papers. The major mechanism in the heart, and this seems to be different definitely from skeletal muscle, is that PI seems to be the important signal. So PI comes in through this transporter. It can also come in through an exchanger, and it obviously through at least mass action and maybe through other allosteric mechanisms activates the ATPase, which is the ATP synthase in the mitochondria. Inorganic phosphate's also a substrate for the TCA cycle. And then all of the in vitro data from purified mitochondria, it turns out we can't explain those data without also activating somehow the electron transport system. And the minimal model, in terms of the fewest number of allosteric interactions that we can use to explain the data, is there's some sort of activation at complex 3. And we put all that in, and we can explain the in vitro data, the in vivo data. Okay, so what do we know about physiological control of oxidative phosphorylation? So the first thing is the metabolic stability hypothesis is disproved. So if you remember the metabolic stability hypothesis, which I'm calling a hypothesis, which is really this single ruling theory of the field, the statement is you cannot explain the data by feedback. So it's kind of a double negative we can not explain the data by feedback anyhow. And so our hypothesis is that if the inorganic phosphate is a key feedback signal. And then something else that comes out of our simulations of the physiological system is going to be important is that the supply side Vmax, okay, the ability to generate ATP is not reached in vivo. And so what's happening is you have some sort of an emergent property where there's a critical value of the free energy at which you can synthesize ATP. And that's what's limiting the ability to consume the ATP in the ATP consuming processes in the heart. So now we can use this model to analyze heart failure. And the way we do that is we take our mitochondrial model, we simulate all of these processes that you see in this cartoon, we put in a cardiomyocyte, and we are also accounting for oxygen transport and flow in a distributed model with advection, diffusion, and transport. We know from some biopsy studies that certain metabolic pools, the creatine phosphate pool and the adenine nucleotide pool and the total phosphate pool are depleted in heart failure. These data come from early left ventricular hypertrophy in the dog model, and then from moderate hypertrophy, you see that the creatine pool has started to go down, basal ATP pool and the basal creatine phosphate pool is going down. And so from these two data points, early and late, we can so that same group, this is Bob Bonke at Minnesota with Jay Zhang, looked at the early LVH case, creatine phosphate, and inorganic phosphate as functions of rate of oxygen extraction. We did something very simple and something very powerful. We took our physiological model, and the only thing we changed in the physiological model was we reduced these metabolic pools according to the biopsy measurements. And so in the early case, here's our model predictions and data. So again, there's no fitting. And then in the more moderate, with greater reductions in these pools, we see these predictions against the data. So again, these are predictions not fit. So we can, with doing something very naive and ignoring all the other possible remodeling that could be going on in hypertrophy, is we just reduce these metabolic pools to the observed levels, and we get a match to the energetic data. And these are all again anesthetized dogs where they're increasing the MVO2 by pacing. Okay. Now we took those two data points, early and moderate. And now we're plotting the creatine pool and the basal ATP as a function of left ventricular body weight normalized to body weight. And the units are grams per kilograms here. Okay, we're going to do something else very simplifying and naive, and we're going to fit a straight line through these two data points. Okay, so it turns out you can do with very low error. Now, and then we're going to use this to predict these pool sizes as a function of progression through hypertrophy as the left ventricle hypertrophies in these canine models. So there's some evidence from an independent study, and this is a pacing model from Joanne Ingwall's lab, that this depletion is fairly monotonic, although there's obviously a lot of individual noise and variability here. And this is the ATP. These are just the adenine. This is just the total adenine nucleotide pool, not the creatine pool. Okay. This is not. These data are not from a pacing model. These data are from Jay's. They include the. They put a pressure overload when the animal's young, and then they over several weeks it develops this hypertrophy. So now we're looking at data from normal, early, moderate, and then which are these black dots, and then these filled circles and these triangles are all individual dogs where the only thing that was measured was the baseline creatine phosphate over ATP. And these measurements now of the baseline, combined with our assumption of this linear decrease in these other pools, allows us to then parameterize the inorganic phosphate pool, which is not directly measured. Okay, so these are all experimental measurements. The rest of these plots now are model predictions of the ATP hydrolysis potential at the observed maximum work rate. And we can see if we just look at there should be a minus sign here. This is the magnitude of the ATP hydrolysis potential, is that the earlier the animals that are doing a little better, that have the end diastolic pressure less than 15 millimeters of mercury, all sort of group at or before this breaking point here, and at the very highly hypertrophied, really failing cases with end diastolic pressure in 50 millimeters of mercury, we have this drop off here, and we see this almost we drew these dotted lines to kind of imply that there's some kind of critical behavior, there's some kind of transition moving from adaptive remodeling to maladaptive remodeling. Now, if we plot model predictions of the magnitude of ATP hydrolysis potential as a function of all these different pools, we can see that the data, so the creatine phosphate pool, adenine nucleotide pool, and exchangeable phosphate pool, we can see that the data kind of follow along this plane, and we can look at that plane this way: total phosphate pool, total adenine nucleotide pool. Again, here are the data points as we're increasing in hypertrophy. And what happens is you've kind of followed this nice contour, and there's a certain amount of experimental variability, and the contours are coming from our model predictions. So, but you can see that what happens at some point, you're either moving up this contour or moving up this hill a little bit, or at least following the contour until you get to some point where you can only drop off the cliff. And you drop off the cliff at a 30% reduction in the adenine nucleotide pool. Okay, and that's interesting coincidence. And this is a quotation from a review by Joanne Ingwall. From human biopsy specimens, ATP and she's not saying it here, but also the total adenine nucleotide pool is 25 to 30% lower in the failing human heart, and why it decreases that much and then no more is not clear. Well, that's sort of an emergent property that comes out of our simulations. That's where you fall off the cliff, and that's where these dogs are on their last legs. So we can look. I'm going to skip this because I stood up. So there's another interesting study recently. Because of the observations of these depleting metabolic pools in heart failure, there's been a certain amount of effort in trying to engineer mice that overexpress a creatine transporter. And overexpress the creatine transporter in order to get the creatine levels to come up in order to counteract the metabolic dysfunction in heart failure. And what happened in this study was they get the opposite effect. That is, if you overexpress creatine transporter in otherwise healthy mice, it causes heart failure as the creatine levels go up. And if you overexpress creatine transporter in already in mice who already have heart failure, you just make things worse. And that happens to be, in hindsight, what our model predicts. And that is, as you deplete the adenine nucleotide pool, moving along this axis, the creatine, the PCR levels are maintained within a narrow range. In the unhealthy myocardium, this is a quote from Wallace, but we find it's true in the remodeling failing heart as well. And so there's a fine balance irrespective of the direction of change. So we would predict that if you are going to have a therapy related to these metabolic pools, then you need to increase the adenine nucleotide pool, not the creatine pool. And of course, if you know anything about the metabolism, that's much more difficult to do. In the creatine case, you've got one transporter to target, but you have a very complicated de novo adenine synthesis mechanism. So really quickly to summarize, we predict there's two distinct phases associated with the metabolic remodeling. We call them adaptive and maladaptive. And there's a critical transition which occurs at about 30% of the adenine nucleotide depletion. You can read about all the details here. Very briefly, I want to at least say Fan Wu's name, because Fan is the person who's really done a lot of the modeling work and on all of these series of papers on the normal heart and now on the failing heart. So thanks a lot.
Well, thanks, Dan. Again, we've got time for one question.
And I wonder if you should be a little more specific about the progression, because I'm sure you know this, the progression of heart failure goes through a phase of diastolic failure before you go into a late phase systolic failure. Where does that tipping point, where you'll be going through that transition occur? Is this the point where you begin to go into systolic failure, or is it later than that?
I don't know the answer to that, and I should know the answer. The only piece of data I have are the end diastolic pressure.
Yeah.
So and this is where Bob Baki and Jay have kind of drawn the line between hypertrophy and failure. I don't know if it's a clinically established number or not, or if it has any meaning, but you certainly don't want to have pressures like that.
No. It's just that the function begins to just suddenly drop off at a period with hypertrophy.
Yeah. Well, these four dogs, I understand, were absolutely on death's door.
Right.
And
so it's probably well into the development of systolic failure.
Yeah. Yeah.
Well, Thanks, Dan. Unfortunately, there's no more time for questions, although I did want to ask about intracellular calcium, because I thought that controlled glycolysis. But anyway, I would like to thank all the speakers for a great session this morning. We now break for lunch. Nick, do you want to say anything?
No, at this point.
Okay, so